Welcome to our second review video for Calc BC, and today's title builds right on top of the limits we did yesterday, and we're going to talk about continuity and differentiability today. So our first piecewise function, we're going to try to find the value of a that makes this function continuous, and on this particular one I'm actually going to take the time to try to sketch this one out, and so that we could visualize what we're attempting to do. The first function, the x squared plus 1, is just a parabola shifted up 1, and it's going to be visible whenever x is less than 0. So we've got an open hole right here, and the parabola swoops in like this. A is unknown, so I'm going to skip that for now, and then x plus 1 is just a linear function, and he'll be visible whenever x is greater than 0. So it'll look, let's see, maybe a little something like that. So basically, we want A to fill in the hole. And this is just a very nice basic one. We know that if we let A equal 1, then it's going to fill in that hole, and we're going to have a smooth, continuous function. And basically, just to review, our continuity means we can completely trace the graph without picking up our pencil. There's no jumps, gaps, breaks, or asymptotes in it anywhere. Here's another piecewise function, and they're just asking whether it's continuous or not. And we're going to use our three-headed monster, the same, we've been using that on quite a bit of our bite-sized quizzes, so hopefully we've got that down pat. We're going to really emphasize proper notation. We have seen things like this creep up on the free response recently, and it was really emphasized last summer at some of our conferences. But basically, we're going to use the less than symbol to identify the left-handed function, and then the greater than sign is going to identify our right-handed function. So go ahead, hit the pause button, practice using good notation, and we're going to prove whether or not this one's continuous. Okay, I'm 2/3 of the way through mine at this point here. You can see here in the top row I've worked through the limit from the left. We just substituted the 3 and I ended up with 30. And then the limit from the right side, well, it was just a value of 30. There was no variable to substitute the 3 into, so it's just 30 again. So things are looking good. And at this moment, we can definitively say that the limit, the undirected limit, does exist. Now, notice we always called it the three-headed monster because there is that third component. We want to now ask ourselves, what is f of 3? We're going to go look at the equal sign here. So we've got 10 times 3 minus 1, that equals 29. Ouch. Okay, that's not good. So we're going to say this one's not continuous because the limit as x approaches 3 does not equal f of 3. And our notation's got to be spot on. It's got to be just like that. Well, here's one more limit or continuity question, and we have the unknown value of k that we want to solve for that would make this piecewise function continuous. So good chance to hit the pause button and come on back and see if you got the same thing I did. So here I'm halfway done. I identified my left-handed function here and my right-handed function. I wrote down my three-headed monster here, particularly for this problem with the limits approaching -3 from the left and the right and so forth. So as far as the left goes, we're going to substitute the -3 in right here. And that, let's see if I clean that up a little bit, I do get negative, or positive 6, I should say. Then the limit from the right is just 6 itself, so that's an easy cleanup. So we really got to just focus on that last one and figure out when does k squared minus 5k equal 6. Notice I didn't substitute the -3 in for the k's. I'm only allowed to substitute the -3 in for the x's. So I've got to set these guys equal to each other and see if we can't solve that for k. So we've got k squared minus 5k minus 6 is equal to 0. We've got some factoring going on here. K plus 1, I believe. So then we've got k could equal 6 or k could equal -1. Okay, we're going to introduce the concept of differentiability, and before we learn any of our shortcuts, we started off with this idea here, and I'm going to ask that you guys use up a hefty size of your notebook, maybe a half page or so, to try to duplicate this drawing. And our red point right here, we're going to call that's x. So we're going to call that ordered pair x comma f of x. Hopefully you've seen this demonstration before, and I hope it's important to be able to follow along. This x coordinate is going to be x plus h, so this gap from here to here is h units big. And then this ordered pair is a long one. It's x plus h is the x coordinate, and then f of x plus h would be your y coordinate. And the idea, see, differentiability came into play because we wanted the slope, the instantaneous slope of that red dot right there. And so the only way to get the slope of that red line was to slowly morph our purple line onto the red line. We want to transpose it right on top of the red line. And the only way to do that is to physically, we want to grab this ordered pair here and drag it closer and closer and closer until it imposes itself right on top of the original point. And so that's where the difference quotient was born. We said, first of all, the slope of that purple line is f of x plus h minus f of x, there's the two y coordinates, divided by x plus h minus x. And then we said what do we want h to do? We want h to get infinitely small. And then of course we cleaned up the denominator and the x's canceled, and that's why we have just h on the bottom. So that's the difference quotient that we know and love, and we're pretty good at it. Well, there is one other twist that we could put on this, okay? And hopefully this doesn't get too messy. They could start to call this c comma f of c, okay? And this red dot down here is still going to be the stationary point. The purple one's going to be the one that's moving and getting dragged closer to the red one. And if that was the case, and we've seen this a few times recently on the exam, they're going to say, all right, we want c to approach x. All right, that means x is stationary and c is the movable one. And then they're just going to set up the slope formula, and they may change the order a little bit, but it might be f of c minus f of x all over c minus x, or vice versa. Or they could even say, you know what, let's do the limit as x approaches c. Now c is the stationary and x is the moving point, you know, and go f of x minus f of c, something like that. And I want you to know that all three of these are synonymous pretty much, and they all represent slope and differentiability. Algebraically, there's a two-part definition in order for a function to be differentiable. Number one, the function, first of all, has to be continuous, otherwise it's a no-go instantly. And the second thing gets pretty tricky as far as the notation. We're going to say, in order for the function to be differentiable at a certain point, such as x equals c, we're going to say the limit as x approaches c from the left side of f prime is equal to the limit as x approaches c from the right side of f prime. So it's just a matter of calculating the function's derivative and then evaluating the limit from the left side of c and at the right side of c. And if that's true, then we can definitively say that x is differentiable at x equals c. But this is something we haven't talked about much yet. That's gonna pop up in a couple of our Good Morning Maths, and I want you to have seen the notation going into that. Here's one of my very favorite problems that we continuously see on the exam, or at least something similar. They want to know for what values of a and b will f of x be differentiable. And of course, differentiability also implies continuity. So we've got two things going on here, and that's how I like to split my paper and kind of organize it like this. On the left side, we're going to entertain the idea of continuity. On the right side, we're going to entertain the idea of differentiability. So if this function is really continuous, then a times 1 cubed minus 6 times 1, because 1's the breakpoint, has to be b times 1 squared plus 4. And then we could clean that up just a little bit here. So that's giving me a minus 6 is equal to b plus 4. Let's see, maybe we'll say a equals b plus 10 for now. Alright, so now differentiability. We're going to take the first guy's derivative, that's going to be 3 times ax squared, and just reinforce that a is just some kind of coefficient, so there's no need for product rule there. Minus 6 equals 2 times bx. We're going to substitute the 1 in for x. So we got our 1 squared minus 6, 2 times b times 1. Clean it up just a little bit. We got 3a minus 6 equals 2b. Now you notice we have a system of equations and two unknowns, which works out great. And what I'm going to do is, since I guess I've already got a isolated, you could have isolated b, it doesn't matter. I'm going to substitute the quantity b plus 10 in for this a right here. Create a little more room. It's going to get a little messy. So we've got 3 times the quantity b plus 10 minus 6 equals 2b. A little fancy algebra here. 3b, let's see, plus 24 equals 2b. How about b itself equals negative 24? And then we'll take that rascal, we'll substitute it in over here, and we could say a equals negative 14. And so if a was negative 14 and b was simultaneously negative 24, then our original piecewise function would not only be continuous, but would also be smooth and differentiable even at that breakpoint at x equals 1.